Welcome again to the official IAU G2 online conference series. Today we have the first special seminar because as you know, normally these talks are oriented to young people in our community, providing their results and also giving them the possibility to have some visibility. But today we decided to invite Nick Wright. He's more senior and he's an expert on many things related to associations, cluster, massive star, but also young stellar objects. And since he wrote last year or a couple of years ago, or maybe even longer, some reviews about OB star associations. We thought that could be interesting for the community that he provide this overview of the main things we know about OB associations in these days. So just to comment about a bit about his career, he did a PhD at University College of London. This was on planetary nebula. So quite a bit of change later. And then he did a postdoc in Harvard, Smithsonian, working on X-ray studies of young star and stellar activity. Moved to the Royal Astronomical Society with a fellowship in Hertfordshire, in the University of Hertfordshire, working now on more things related to what he's doing now, cluster and association dynamics. And nowadays he's Ernest Rutherford Fellow at Keele University, where I think you have more or less stabilized, no? And talking about his interest, quite broad, going from stellar dynamics, especially related to star cluster formation and evolution, also galactic structure and the star formation history in the Milky Way, stellar activity, also related to rotation, and he is contributing and will contribute importantly to the next generation spectroscopic service with both WIF and FORMOS, and maybe he will be talking a bit about that in this talk. So thank you very much, Nick, for accepting our invitation, and we are really looking forward to hear what you want to tell us. So whenever you want.
More technical difficulties, but we are working again. Thank you everyone for joining. Yeah, I'm Nick Wright. I'm no longer a young astronomer, but I do appreciate the opportunity to come talk to you today. Yeah, I'm based at Keele University. If you go on to the next slide, for those who've never been to Keele, we are a small, primarily teaching university in the Midlands of England, about halfway between Birmingham and Manchester, built around a very beautiful countryside campus. If you're ever in the UK and in the area, please let me know, and you're more than welcome to come visit, and we can arrange a seminar for you. If you go on to the next slide, what I'm going to present today is summary of a couple of review articles I've written in the last few years on OB associations, going over their history, their recent role, and their sort of current role in modern astrophysics. Next slide. I'd like to thank these four people: Simon Goodwin, Rob Jeffries, Marina Kunkel, and Eleanor Azari, because they helped write Protostars and Planets review that was presented in Kyoto in April of this year by Marina and Eleonora. If you go on to the next slide, I'd also like to thank those in my research group, either recently or currently. I'm going to try to present some of their results as well as historical information about OB associations. Next slide, please. So the vast majority of young stars are found not by themselves, but in groups or clusters of some sort. And I've put up some examples here to show you a sort of selection of the sort of groups and clusters that we find in our galaxy. In the top left is what we might think of as a low mass star forming region or star cluster. This is Rho Ophiuchus. It's relatively low mass. There's several hundred stars there, about 100 solar masses of material. Nothing particularly more massive than the sun. No OB stars, nothing that's going to really affect the environment. And the density is quite low. So it's quite a gentle, pleasant environment for a star to grow up in. If we go up an order of magnitude, then in the middle, we've got the Orion Nebula Cluster, which is the nearest region to the sun, where stars are still forming and where we'll find a massive star. And there are a couple of O stars and multiple B stars in the ONC. There's about 10 times as many stars here. So we're looking at about 3,000 or 4,000 stars, about 2,000 or so solar masses. And so you've got obviously a much more extreme ultraviolet radiation field. And the density is higher because there's more stars, but the region of space is naturally that much bigger. So that means higher density, more close encounters between stars. So the environment's getting a little bit more extreme. If we go up an order of magnitude again, then on the top right, you've got one of the young massive clusters in our galaxy. This is NGC 3603. It's about 10,000 solar masses of stars, 20 or 30,000 stars there. And in a cluster like this, you're finding tens of O stars, 20 or 30, I think, in this cluster, several hundred, if not thousands of O and B stars. So a very extreme radiation field. You're going to get strong stellar winds, supernovae that explode before many stars have even finished contracting onto the main sequence. And again, more stars, but not too dissimilar a volume of space. So the density is higher. So much more extreme environment than the other one. And this sort of represents the star forming regions we find in the Milky Way. But if you go to a massive galaxy with a starburst galaxy, for example, you'll find clusters several orders of magnitude bigger even than this. Now, despite the vast majority of stars being in groups or clusters, most young stars are actually found not in these dense concentrations that we see and think of as clusters, but in associations. Next slide, please. This one is the Scorpius-Centaurus OB association. This is the nearest OB association to the sun. It's got about 150 B stars. It has, I think, one O star, which is escaping from it. And it's about 80 degrees across on the sky. So it occupies a huge area on the night sky because it is at a distance of 100 to 150 parsecs, and it's about 100 parsecs across in total. So this is a very, very large region. It's about got the same stellar content as the Orion Nebula cluster. So a couple of thousand stars in there in total. We don't notice it because the density is so much lower compared to clusters. Next slide, please. And this is an example of one of many OB associations in our galaxy. Probably three of the most prominent that you may have heard of are SCO-CEN, which is the nearest OB association, the Orion OB1 association, which includes many of the star-forming regions in Orion that you're probably aware of, and Cygnus OB2, which is the most massive association we know of in our galaxy, and is sort of comparable in size to the young massive clusters I talked about. A broad definition for associations, which does come from sort of the original works that I'll be talking more about, is that OB associations are low density and gravitationally unbound. They're groups of young stars, and while they're often delineated by their brightest OB members, they do contain low mass stars too. They contain a full mass function of stars, just like any other cluster. Next slide, please. So why would we be interested in studying OB associations? Next. The first reason is that there are some theories of star formation that suggest that the star formation process is affected by density. For example, the theory of competitive accretion suggests that as stars are beginning to form and they form into little groups and protoclusters, the gravitational potential caused by that forming cluster of stars allows gas from the surrounding molecular cloud to be attracted to that protocluster, accrete onto the cluster, and accrete onto the star, the protostar that's forming in the center of that protocluster. That star ends up with a competitive advantage, and so it competitively accretes more than the other stars. And that is the idea by which some of the most massive stars gain more mass than their other stars. Again, this is competitive accretion and compares to sort of the other contrasting models of core accretion, where it's the properties of the core rather than the environment that set the mass function. Next. The other reason that you might be interested in studying OB associations is that because they are significantly lower in density than in star clusters, this means that binary systems, protoplanetary systems, and planetary systems will all be affected by that lower density. or less affected, if you will, compared to had they formed in a cluster. We know that protoplanetary disks get evaporated when they're in the proximity to massive stars. We've seen this both visually directly in Orion and in many other clusters. We can also see it quantitatively in numerous OB associations and clusters. So we know that stars get affected, and we know that the rate at which they get affected is due to their proximity to massive stars and effectively the ultraviolet radiation field that they experience. We know that binary systems get affected by the density of their environment. Binary systems can get disrupted by close encounters, and I think it's reasonable to assume that planetary systems would be as well. So the formation of all of these systems is going to be affected by environment. Next. The other reason we're interested in OB associations is that these are dispersing gravitationally unbound systems. And in that sense, they are a contrast to open clusters, which probably arise from broadly similar conditions, we think, but go on to be gravitationally bound and long-lived for tens, hundreds, or thousands of mega years. And we've used open clusters for much of the last century as a really important astronomical tool for understanding stellar evolution. They've been utterly vital, and they continue to be for many areas of stellar evolution. And they're probably going to be even more important in the next century as we use them to study planetary evolution, both individual planets, planetary atmospheres, and planetary systems, because they're really the only place where we can get a very strong estimate of the age of the system that is very reliable. But if we're going to use open clusters as an astronomical tool in that way, we need to understand why only a small percentage of young clusters end up as gravitationally bound and long-lived open clusters, while the vast majority disperse and are visible as OB associations. So OB associations are useful for understanding the dispersal of systems like that. Next slide, please. And finally, OB associations are a really useful way for tracing galactic spiral structure. I'll be talking about this a little bit more. We can obviously use young stars, OB stars, stars in any sort of form, but OB associations offer the advantage, like with star clusters, that you can get better estimates of the total age and kinematics of the system, which allows you to better trace galactic spiral structure and how it's evolved over time. Next slide, please. So I would just like to go over some of the history of OB associations, and this is, I'm afraid, going to be a dry few slides. Ambartsumian is famous in 1947 for identifying associations for the first time and defining the term. He defined it as a new type of stellar system, and at the time this compared to open and globular clusters, and he recognized that they shared some similarities, but obviously they were different in that they had a lower density. Next. In a follow-up paper, he noted that given their low density, which is sort of typically lower than the actual gravitational field star density, then they must be gravitationally unbound, and therefore they're likely to be expanding. Next. The next person to enter the field in terms of OB associations was Blaauw, who in the 1950s studied multiple OB associations. And one of his conclusions was that because they were gravitationally unbound and expanding, they may have already undergone some expansion. We were unlikely to be observing them at the beginning of their expansion. And based upon that, they might have occupied a smaller volume in the past, potentially have been more like a cluster, for example. Next. And he noted many other correlations that supported this. For example, the larger associations he studied were less likely to be associated with interstellar material than the more compact associations. And the larger associations also seem to have older stars than the more compact associations. So he could see an evolutionary pathway going from smaller associations to larger associations that supported this evolutionary picture. Next. Around this time as well, the sort of growing numbers of OB associations that were being studied were collated by Ruprecht in 1966. And it's thanks to him that we have the sort of current enumeration system for OB associations, where they are named after the constellation they're found in, and then have a number depending on when they were discovered. So we have Orion OB1, Orion OB2, Cygnus OB1, 2, 3, 4, etc. And he was the first person to organize and collate that system. Next. Jumping forward, I think the next person who made a serious contribution to OB associations was Roberta Humphreys in the late 1970s and early 1980s. They were cataloging luminous stars in OB associations for the purposes of studying systems in other galaxies. But in doing so, they were able to get a better estimate of the luminosities of OB stars, and in doing so produce the first detailed census of the OB members of OB associations, and that census has pretty much remained to this date. Next, please. Jumping forward, the next sort of revolution comes in the 1990s by a predominantly Dutch group who used data from Hipparcos to study nearby associations. Examples here include Deseo et al. Paper in 1999, which provided a census of more low mass members, but also obese members as well, in some of those nearby associations. And works, for example, by Brown et al., De Bruyne and Hugerwerth around this time expanded our understanding by using Hipparcos astrometric data. Next, please. And then the sort of final part of this history comes in the early 2000s, where predominantly spectroscopic surveys, but also X-ray surveys, allowed us to expand our census of the low mass members of OB associations. There's quite a lot of people who contributed in this area. There's a good review by Briceno et al. In 2007, but notable papers by Mamajek, Prybish and Jeffries around about this period. Next. And this brings us up to sort of the current day and the current revolution in our understanding of OB associations, which is brought about by a revolution in kinematic data, quality and quantity. And this is brought about by two things. The first is a huge increase in the number of multi-object spectroscopic surveys that are providing us with radial velocities. The Gaia ESO survey was one of the pioneers of this, but there are also the STSS surveys, the upcoming surveys with WEAVE, with Foremost, and future facilities such as the Mauna Kea Spectroscopic Explorer. And these provide us not just with stellar parameters about individual stars, they can provide confirmation of youth, but they can also provide radial velocities. And those radial velocities can be combined with astrometry from Gaia, which I'm sure we all know about, provides positions, parallaxes, and proper motions. And once you combine data from these facilities, you've effectively got three-dimensional positions and three-dimensional kinematics, as well as complementary spectroscopic information. And that's really vital for studying these very low-density systems where it isn't always easy to pick out the members of the associations. Next. So in my review in 2020, which was the first of the two reviews that I'm sort of summarizing here, I put together an attempt to collate the existing census of OB associations, compiling work from Ruprecht, Humphreys, other studies in the 90s, Garmany and Stencil, Melnick and Ekstromov, and Deseo et al., and sort of divided the known lists of associations into sort of three categories. The first was a sort of short list of well-studied associations, associations where there are good knowledge about the members, where we are absolutely certain the association is real. And there's about 5 of these. SCO-SEN, Vela, Orion, Cygnus, Trumpler 10. These were all, without doubt, very important systems to study. There's then a sort of second category of what I referred to at the time as high confidence associations, systems that we're pretty definite are real, we have a moderate amount of information about. And then another extended list of sort of very poorly known associations where perhaps their existence wasn't entirely certain. Some people are uncertain exactly of the membership of them, and perhaps have been identified but not followed up on in the literature. If you go on to the next slide. As it turned out, a lot of what I included in my high confidence list of associations may not be real either. And this is work from my PhD student who's recently graduated, Alexei Quintana. He revisited the membership of a number of existing associations using Gaia data to see whether they were genuine. And what he's showing here is the kinematics, proper motions in the top panel, and distances as a function, both as a function of galactic longitude, for the known historical members of the 5 most prominent and massive OB associations in Cygnus. And as you can kind of see from the bottom panel, while most stars are around about 1.5 to 2 kiloparsecs, there's certainly a large amount of contamination in all those samples, foreground objects and background objects that certainly aren't members. Even if you were to exclude them, there is certainly a spread that is considerably larger than one would expect. I mean, if you look at SIG-OB3 on the right-hand side in red, you can see that the OB stars there cover more than 500 parsecs in distance, and their parallax errors aren't large enough to explain that. And that would seem to be unphysical, given they only occupy about 50 parsecs on the plane of the sky. In terms of their kinematics in the top panel, while they are all broadly moving in the same direction, this is mostly due to the motion of stars in the galaxy and the sun's motion. If you actually look at their kinematics, they don't really appear to be moving in the same way, in a way we would expect. The exception to this is probably SIG-OB2 in green on the left-hand side, which does appear to be real. But Alexei concluded that these were probably not real groups and merely an overabundance of OB stars on the sky. Next slide, please. What Alexei went and did is to see if he could find the real OB associations, because there are a lot of OB associations in this area of the sky. He designed an SED fitting tool to identify OB stars, and then used some clustering tools to group them into OB associations. And these are the OB associations he found in that area, all at a similar distance of about 1.5 to 2 kiloparsecs. In green on the left is SIG-OB2, which does exist as a clear group in both spatial coordinates and in kinematic coordinates. But you'll see that the associations that he's proposing, the other colors groups on this plot, don't really match up with the historical ones. And Alexei has gone on to repeat this in other constellations around the sky and is now doing a full sky mapping of OB stars and OB associations. And unfortunately, the conclusion is for the vast majority of OB associations, let's say that are beyond 1 kiloparsec, they potentially have some truth in their core, but the membership lists that you can find are probably not reliable, and their membership and existence does really need to be revisited. So certainly some work to do in that area. Alexei, by the way, has recently graduated. He's been awarded his PhD. He's got a short postdoc lined up, but he's on the job market. So if you're interested in somebody who has expertise in astrometry and photometry of OB stars, let me or him know, and he'd be interested to hear. Next slide, please. So this is just an attempt to show you where the current OB associations are on the plane of the sky. Obviously, the existence of each of these individual associations is not guaranteed, but they are an indication of where there are concentrations of OB stars. Next. The main group we can see here is SCO-CEN, which is composed of sort of 3 small sub-associations, upper SCO, upper Centaurus Lupus, and lower Centaurus Crux, going from a galactic longitude of 0 to around about 280, so a huge expanse on the sky. Next slide. You can also see here smaller, at least on the plane of the sky, associations. Obviously, they're of a similar size, but they're further away. These are part of the Sagittarius spiral arm at about 1 to 2 kiloparsecs distance. Next. Moving around on the sky, next, you can see the Cygnus associations appearing here. Again, their membership is being revisited, but those are all at around about 1 to 2 kiloparsecs. Next. Next again, sorry. And then this is further around on the sky. We've got Orion OB1 there next, and then Vela OB2 here. And this is just to give you an idea of where the concentrations of young stars, OB stars, and OB associations are on the sky. Next, please. This is another attempt to visualize the historical census of OB associations. So this map is composed of the historical list of OB associations that dates from Ruprecht and Humphreys et al., which I took in my review, and I obtained average Gaia distances for all these using one of the Melnick and Efremov's papers on this topic. And then I basically mapped them onto the galactic disk and superimposed this famous image, artist's impression of the galactic disk, which comes, I think, from the Spitzer period of time from NASA. And you can obviously see there's quite a remarkable agreement between the distribution of OB associations, or more likely the distribution of OB stars, and the spiral arm structure of the Milky Way, which is quite impressive given that these OB associations were sort of first identified 40 or 50 years ago. Next. Here's where I'd sort of put those three spiral arms next. And you can see that these are the Sagittarius arm, the local arm, and the Perseus arm. And this is just to give you an idea that these associations really do follow the spiral arms quite closely and could potentially be used to map out spiral arm structure. Next, please. So I'd like to talk a little bit about how we currently go about identifying members of OB associations. In terms of the OB members, classically this was obviously done with blue end photometry, U, B, and V. And this is a technique that has continued into the modern age. This is from Mike Moore-Smith's work using VFAS plus photometry, U, G, and R to identify OB stars. Because the OB stars don't redden onto themselves, they trace out a unique area of these color diagrams, allowing them to be identified quite effectively with an estimate of extinction. Next. This is the similar sort of technique that my PhD student Alexei used, but he took it one step further, folding in Gaia parallaxes, evolutionary models and stellar atmosphere models, and then put it into a forward model Bayesian inference framework. And he's used this to basically fit the astrophotometric data for all OB candidates in the galaxy, comparing them with evolutionary models and getting estimates, posterior estimates of the mass and age, as you can see on the right-hand side HR diagram showing where this object is. Next. In terms of low mass members, it's obviously a lot harder to identify these because at the typical age of OB associations, which is sort of between about 5 and 25 mega years, young low mass stars don't have prominent protoplanetary disks around them in abundance, at least. They don't show H-alpha excesses, so they're a little bit hard to identify. Thanks to Gaia, we can identify the pre-main sequence in an absolute color magnitude diagram, as shown on the left, a figure from Zari et al. 2019. And that is a reasonable way to identify candidate low mass stars. But we do then need to spectroscopically verify them because there can be a lot of contamination. And one of the strongest methods to do that for low mass stars is to identify the presence of lithium. Lithium exists in stars as they form, but is destroyed at the bottom of the convective envelope at the beginning of the pre-main sequence. But it can survive for between sort of 10 and 100 years for stars between about 0.5 and 1 solar mass. And so it offers a really strong indication of youth in low mass stars. And it's probably the gold standard for confirming the youth of low mass stars. Next, please. Based upon sort of studies like that, we've built up more and more improved censuses of OB associations, and we're getting a better idea of their total size and structure. And one of the things that we see is that they really are part of a larger scale hierarchical structure. And I want to show this figure from Guglielmis 2018, showing sort of that hierarchy of structures that exists on multiple scales. On the left, we've got the Cassiopeia OB6 association, which has been known about for many, many years. And that's actually shown on a WISE image showing you the infrared molecular clouds in this area. In the middle is a zoom into one part of that, the W3 star forming region, which is one part of Cassiopeia OB6, and where you've got a single molecular cloud that's beginning to form stars. And on the right, you've got an embedded cluster within that molecular cloud, within that OB association. So you see you get a hierarchy of structures where OB associations often end up being sort of the largest structure before you get to that of spiral arms. Next, please. The structure of associations themselves ends up being very, very substructured. There are multiple subgroups. There are stars at different densities, and it's quite a complex structure when you start to zoom into these in a bit more detail. This is the SCO-SEN association with its 3 subgroups, which are labeled on here. And this is a census that Damiani et al. Put together based upon Gaia data. The black points show the OB stars, if I remember correctly. And the color map on the background shows you the distribution of low mass stars that he'd identified using Gaia. And you can see that while there's a sort of broad low density distribution across the whole region, there are also over densities, particularly in the youngest bit, upper SCO in the top left, but also across the other 2 associations. So you've got this sort of complex hierarchical structure with multiple different subgroups that exist. Next, please. One of the other important things to do with AOB associations is begin to determine their ages. We can do this obviously with both post-main sequence ages for massive stars. This can be very effective if you've got enough objects in your sample, but is kind of limited by our current ability to model mixing, mass loss, and binarity in these systems. For low mass stars, now that we've started to detect them in large numbers, we can determine pre-main sequence ages. But again, this is also slightly limited by our modeling of things like radius inflation, rotation, and magnetic activity, all of which affect our ability to derive ages from HR diagrams or absolute color magnitude diagrams. But there's a lot of ongoing work in this area, as well as attempts to use the precise abundance of lithium in these stars as an age indicator. And this work in the bottom right here is an empirical model of lithium predicted as a function of age from Jeffries et al. 2023. And you can see there the predicted amount of lithium between about 5 megayears and 5,000 megayears for stars with quite low temperatures, but ones that we can study in large numbers. So if you go to the next slide, please. Once we've got ages, we can begin to look at ages, age spreads, and age distributions. So this is SCO-SEN again, with the 3 subgroups. This is a paper from Picot and Mamajek 2016, showing you the age of stars. And you can see that there's quite an age gradient across the association, going from sort of 5, 6, 7 megayears in upper SCO on the top left, down to 20 or 25 megayears in lower Centaurus crux on the bottom right. But there's also substructure. There's individual groups that show a different age to their surroundings, and it's quite a complex age pattern that probably echoes that spatial substructure that we saw. Next, please. In terms of kinematics, now that we've got Gaia data, we can also look at the kinematic substructure. And again, we see a similar level of complexity. This is from my paper in 2018 on SCO-SEN again. And you can see that we've got 3 different subgroups there. And I've color-coded the proper motion vectors according to the position angle of their motion. So you can begin to see that stars, for example, in upper SCO share a different motion to that in lower Centaurus crux or in upper Centaurus lupus, but that there's also differences across individual subgroups of the association. Next, please. And one of the things that we can start to do with kinematics is we can look at the expansion of these groups. This is something that is a sort of growing industry of. You can do this both qualitatively, as shown in the bottom left, by obviously looking at the proper motion vectors on the plane of the sky and seeing a clear expansion pattern. This is for one of the Vela OB2 subgroups. But you can also do it for your individual associations. There's an example there from Alexei Quintana's work in one of the Cygnus OB associations. And on the right, my PhD student, a previous PhD student, Joe Armstrong, who did a detailed study of the low mass members of the Vela OB2 associations, finding very strong evidence for expansion. The sort of expansion gradients I'm showing there are position versus velocity, which is an indication of expansion. And this is really one of the powers that Gaia gives us, because we're measuring velocity in the plane of the sky where we've already got spatial information. We can get a correlation between position and velocity, and that means we can start to be thinking about accelerations and forces being at work. And that's one of the real powers of Gaia. Next, please. This is just a recent example of some work I've been doing extending this study of expansion to more embedded and younger clusters, where we looked at a sample of clusters from the Gaia ESO survey, and we found that 94% of the clusters studied by the Gaia ESO survey, all but one, were in the process of expanding. So this expansion of these stellar groups starts at a very, very young age, within about 1 to 2 megayears of formation, and it then exists throughout their sort of embedded cluster phase, their young cluster phase, and throughout their OB association phase until they sort of disperse and are lost in the galactic disk. Next, please. One of the things we do notice, however, is that the vast majority of clusters and associations are expanding asymmetrically, meaning they're expanding at different rates along different axes. The classical explanation for the expansion of these groups is called residual gas expulsion, and it suggests that a star cluster is perhaps in gravitational equilibrium or close to being bound when it's in a molecular cloud, because it's held together not just by the potential that comes from the stars, but also from the gas. But then when feedback disperses that gas, taking away the vast majority of the mass, because star formation efficiency is quite low, it also takes away most of the gravitational potential, and the system expands and disperses. And this has been the historical explanation for the dispersal of young clusters. But it predicts a symmetric expansion, and yet most clusters and associations, it appears, are expanding asymmetrically. And this is probably due to the effects of the surrounding gravitational potential well of the wider molecular cloud. But it does need to be something that we investigate further if we're going to retain residual gas expulsion as the dominant mechanism for the dispersal of these systems. Next slide, please. So in terms of how OB associations form, we see that most associations are broadly dynamically unevolved. They've got physical substructure, kinematic substructure. Their velocity dispersions are anisotropic, meaning they're different along different axes. They don't appear to be mass segregated. And these are all signatures of a system that hasn't really had a chance to mix, because when you do dynamically mixing of groups of stars, you erase physical, kinematic, age substructure, and you approach isotropic velocity dispersions, and you can develop mass segregation. So the lack of all these things suggests that these are not mixed groups of stars, and suggests that they probably formed with a similar sort of spatial and kinematic configuration as we currently observe them. So if we observe a subgroup in an association, that probably formed as some sort of subgroup within a wider group of stars and hasn't been mixed up since then. Next, please. There are a number of theories for the sort of propagation of star formation across OB associations because of their large scale. There's the classical model of Elmer Green and Larder from 1977, that the ionization of massive stars triggers star formation. And this has been particularly applied to OB associations and OB subgroups quite a lot. Next, please. So a more recent example put forward by Krauss et al. In 2018 called the surround and squash model, in which superbubbles begin to squash molecular clouds and lead to the triggering of star formation. Next, please. And that's sort of related to the sort of supernova acceleration of H2 regions, as shown here in the Vela region, in which feedback from a previous generation of stars would accelerate an H2 region and trigger star formation in it. Next, please. This is a study from Grosch et al. In 2021, in which they looked at the motions of molecular clouds and groups of stars in the Orion OB1 association, the wider Orion complex, and looked at the motion of all those groups and found that they were all actually moving away from one common center. And it's this sort of kinematic information, as well as spatial age gradients, that are often used as an indicator that there is some sort of propagation mechanism that propagates star formation on these larger scales. Next, please. I will add, however, that my PhD student did some investigation into this and actually found that the kinematics of these groups don't require any additional injection of energy. Their scale of their kinematics and their physical scale is completely consistent with Larson's laws of offsetting kinematic motions within molecular clouds, and suggesting that if these groups just simply formed out of a single molecular cloud, they would naturally expand and disperse away from a single point, because expansion always leads to that preferential radial expansion pattern, and you don't require any extra injection of energy, which I think is quite in contrast to the tendency of people in association studies to want to pin some sort of propagation model, some sort of age gradient on the propagation of star formation. Next slide, please. This is just an example of looking at the larger scale kinematics of OB associations. This is in Cygnus, where we identified those 6 new associations. And here, the proper motion in galactic longitude is shown against galactic longitude, showing these 3 large expansion patterns. Next slide, please. There's 2 sets of associations here. There's 3 on the left-hand side with ages of about 3 to 5 megayears, and 3 on the right-hand side with ages about 10 megayears. They're clearly kinematically connected because they share this correlation between position and velocity. And when you group them together, they do form 2 groups with distinct similar ages. This is really interesting because this shows a sort of large-scale kinematic expansion pattern existing on scales of about 150 parsecs and about 25 kilometers per second. And this is potentially driven by that seeding of motions from things like Larson's laws that then ends up dispersing as these groups and forming these large-scale kinematic expansion patterns. Next, please. So before I finish, I'd just like to talk about some of the implications of our sort of current understanding of OB associations. The first returns to the topic of the photoevaporation of protoplanetary disks, which we know occurs from radiation from OB stars and is one of the dominant influences of OB stars on low-mass stars. We know that this affects scales with density, so we'd expect this to be less effective in OB associations. And these are some figures from Guarciello et al. 2016, which is a study of the fraction of stars with disks in the Cygnus OB2 association. On the left-hand side is the disk fraction shown for different subsets of stars in SIG OB2 as a function of their far ultraviolet flux that comes from the OB members. And in the right is showing you a visual illustration of where those stars are. So stars close to the OB stars are in blue. They have a high FUV flux. And it turns out on the left-hand side, you can see they've got a very low disk fraction. Whereas you move to lower and lower FUV fluxes, so you move away from the OB stars and you move to the left on the left-hand plot, you see the disk fraction increases. So there's a very clear correlation in a single environment here that the fraction of stars with disks is immediately affected by the density of OB stars. And this is important because it means that in these low density associations, there's going to be a higher fraction of stars with disks, and that's certainly going to affect the properties of the planets that form in those disks. It might mean more planets, it might mean larger planetary systems, it could mean a number of things, but it's certainly an indication that disk fractions are lower. Next slide, please. We also know that multiple systems get affected. One of the notable things that's been observed in Cygnus OB2 is that there's a huge abundance of very, very wide binaries. And it's believed that the only way that this can occur is if the association had never been particularly dense, because we know that dense regions end up disrupting wide binaries. They get very easily disrupted. And so the presence of very wide binaries might be very, very common and diffuse associations. And this could lead to evolutionary patterns whereby OB stars that form in low density environments have different binary properties to those that form in high density environments. And this can obviously affect a number of properties such as their evolution and their rotation rate. Next slide, please. Talking about future prospects in the field of OB associations, we're obviously looking forward to the multi-object spectroscopic surveys that are coming up over the next few years. We've foremost and STS-S5 will all produce huge numbers of spectra of both low and high mass stars in associations and outside of them over the next 5 to 6 years. Just showing here the density of targets for example, the SDSS YSO program and the foremost survey of young stars, which is mapping out young stars within 500 parsecs of the sun, giving you an idea of the sheer wealth of data we're going to be getting there on stars of all masses. Next slide, please. Also very, very useful, of course, is a number of surveys that will provide us with better data to identify low mass stars in OB associations. eROSITA, even though it's not fully run to completion, has produced data that will allow us to identify low mass members of associations because of their enhanced X-ray activity early in their lives. And LSST will also be effective for identifying young stars, probably both high and low mass, based upon their enhanced variability that occurs at a young age. And both of those are really going to help us identify candidates in associations, improving our censuses and allowing us to do better science. Next slide, please. Looking forward to Gaia. The current Gaia schedule, I think, lists 2 data releases. They are becoming less and less frequent now, which is, I think, allowing us to delve into the data in a little bit more detail before the next data release comes along. Probably in about 2 years, we're going to get Gaia DR4, which will have an increase in the precision of parallaxes and proper motions, which is obviously great. But one of the things that a lot of people are looking forward to is that they've announced that they're going to release all epoch and transit data for all sources. And that will allow people to go in and look at the individual data and better understand the photometric and astrometric evolution of individual sources and potentially fit their own models. Then we've got a 5-year wait till Gaia's probable final data release, the end of mission release, which is going to include a huge amount of complementary data, including higher precision parallaxes, proper motions, and full epoch data in what they're calling the complete legacy archive. But that's quite a way away for a lot of us. Next slide, please. So my summary slide. OB associations, they are young systems, they're low density, and they're important for understanding star formation as well as the evolution of clusters. We've really had a revolution in the last few years, thanks to data from Gaia and multi-object spectroscopic surveys that are really enhancing our view of these systems, both in terms of the number of objects that we can study and the properties of those objects. We found that associations exhibit huge amounts of spatial, kinematic, and temporal substructure. They have age spreads and they don't appear to be dynamically evolved. And all of this suggests that they didn't really form as dense, massive clusters that have since expanded, but formed more as extended and substructured groups, sort of evolving effectively without many interactions to how we see them now. We see that associations are mostly not expanding on global scales, but their kinematically identified subgroups are expanding. That's an indication that they are in the process of dispersing. Attempts to look for propagation of star formation in associations have not really found any simple picture, but there are numerous theories for how star formation might propagate within them. And this obviously has huge implications for star formation in low density environments for both low and high mass stars. So I think I'll finish there and take any questions. Thanks.
Okay, thank you very much, Nick, for this very nice overview. And now it's time for questions. So I see here Jesus already wanted to ask something. So please, Jesus, go ahead.
Can you hear me?
Yeah, now.
Yeah. Hi, Jesus.
Hi, Nick. Great talk as usual. I usually like your talks very much. So, I mean, I think one of the basic conclusions, which is what I've been actually trying to communicate myself, is the fact that this original picture that everything forms in a cluster is not true. I mean, that some people try to sell these associations as expanding cluster, right? And I mean, I think that should be emphasized. I mean, not every star forms in a cluster, and the complex kinematics that you see here is basically shows that, right? I mean, you would need to have very fast expansions to actually contract all these associations into a single cluster, right? But having said that, I mean, of course, I need to sell one of the papers we published in which we found a counterexample of that, which is what happens in the North American nebula. And there you do have a cluster that has, and probably not due to gas, but due to the fact that it has lost, due to dynamical encounters, a large number of massive stars. And that one is actually expanding and quite fast. And if you were to look at that object in a few million years, it would look like an association. So you can have the two things. I mean, it's not only one single mechanism. I mean, do you agree?
Yeah. I think sort of 10, 15 years ago, many of us looked at associations and thought this is the remnants of a cluster that's expanded. And then, thanks to Gaia and thanks to numerous studies like the ones you pointed out, we're now in a picture where we see an association as a collection of subgroups that probably looked like embedded clusters 5 or 10 megayears ago and have since expanded, as well as some sort of distributed low density stars. So it's like stars are forming at a range of different densities. Some end up in clusters like the North American Nebula, some maybe low density groups that we might see around low mass star forming regions in the solar neighborhood. And they're all together in similar areas of space. And if you give them 10 megayears and they're moving at a couple of kilometers per second, then they can quite easily cover 20 or 30 parsecs. And the stuff all begins to overlap with other stuff. And it gets quite complex and messy. And I think we're now, with the kinematic information, beginning to understand that substructure and see that and be able to trace it back a little bit better. So yeah, I agree.
Okay, now we can go to Artemio, please.
Thanks. Can you hear me?
I can. Yeah. Hi, Artemio.
Okay. Hi, Nick. Very nice talk. Thank you. A question: do you find correlation between the spatial position of the stars and the age within the association, so that we can finally say, okay, the association has an age spread, but this small group here probably share the same age and can be studied as a coeval group of stars. Is that possible?
Yes, definitely. I sort of hinted at this with some of the figures I showed on SCO-SEN, Picot and Mamajek, for example, and Damiani et al. I showed those. I wanted to show those because they show the same region from the same perspective. So it's kind of interesting and easy for people to see. There have been some recent papers coming out of the Vienna group by Sebastian Ratzenbrock and Josefa Groschedel, where they've used a combination of spatial and kinematic information to better identify groups, allowing us not to get confusion along the line of sight, allowing us to separate groups that are projected against one another but have different kinematics, and then determine ages for those. And they see quite strong correlations between the ages of stars in one group and their spatial and kinematics, and then differences with the neighboring group, which has different spatial and kinematics and different ages. So we're starting to see it. And SCOSEN is a real great playground for this because it's so close. It's 100 parsecs away. The OB stars in SCOSEN are kind of saturated in Gaia. It reminds you how close it is. But over the next few years, we'll be able to take that to Vela and Orion and the other nearby associations. It will be possible for the more distant associations, but it's going to take time and other methods to perhaps separate stars. But yeah, it is definitely happening.
Thank you. Very interesting.
Lydia?
Hi, can you hear me?
I can. Hi, Lydia.
Thank you for a very, very interesting talk. I have a question. Can you comment what is forming first or simultaneously, low mass stars or high mass stars? I understood point about the disks, but disregarding the observational appearance. So is it inside out or?
In terms of low mass versus high mass, my understanding of the literature at the moment is we don't know. That both, we don't have a good enough, I think mostly we don't have good enough constraints on the ages of stars. There will often be papers that say it looks like these OB stars are older than the young stars, suggesting one formed before the other. But I personally don't trust the age scales enough, certainly in an absolute sense, to confidently say the low mass stars formed first here and then the high mass stars. My understanding of the star formation simulations is also that they don't see a significant difference. Obviously, if it's a simulation of competitive accretion, then you might have a low mass star that finishes accreting, and then a high mass star accretes for a little bit longer, so it can accrete more and end up as a high mass star. So inherent in that theory is that the high mass stars might be slightly younger. Simulations of feedback as well might require that if the feedback is very effective, that the high mass stars are forming slightly later. But I don't think there's a strong set of observational data to support this yet. In terms of inside out, in terms of a cluster as well, I've seen data that goes both ways. I've seen people where they say the bits in the center are youngest and the bits on the outside, and vice versa. And it's still really difficult to say. There's so many biases. When you're studying stars that are on the outside, they might have been kicked out. So that might affect their disks, it might affect their accretion, which means affecting your sample of stars. It might be they're falling in, so they might be from a completely different star forming region and unrelated. It's really tricky, unfortunately.
Okay, any other question? Good opportunity to ask Nick. If not, you can contact him by mail. I have one question myself, just curiosity. So I assume despite this, they are called OB association. Obviously, you are including many more stars in your studies, in your kinematical studies and membership and everything. So how down can you go in mass in this type of studies? So when in the plots you were showing, you go up to A stars, A means equal star, G, or?
In some of these studies, they're hitting the subsolar limit. So, for example, in SCOSEN, Gaia can detect stars down to brown dwarfs. So it is, I would say it's definitely true that every object in SCOSEN above 0.08 solar masses has been observed. Whether we have fully identified it as a member of SCOSEN is not clear because, incompleteness and contamination. But Gaia goes deep enough that in the nearby associations, we should have observed everything. You also got to remember that we don't have high extinction in some of the nearby associations, so SCOS N is effectively unobscured.
And all the stars are providing interesting information for these kinematical studies, or is only the intermediate to high stars and the rest are there and just confirming things. So what do you think about all these lower mass?
They're all good. This audience probably won't like it if I say that the low mass stars are sometimes a little easier to study kinematically than the high mass stars. You can get slightly better radial velocities from low mass stars than for high mass stars, given the line widths. And you don't have to worry about binarity as much. You've obviously got to take into account that all stars, sorry if there's a baby crying in the background, you obviously got to take into account that you know, a decent fraction of all stars are in binaries, but the fraction is so high in OB stars that you definitely need to be aware of that and taking that into account. But we do at all masses model the effects of binaries on any kinematic study.
Okay, and this then goes to my second question, is taking into account all the binary effects that we have in the high mass domain, to derive ages of these associations and the cluster, what is the highest mass that you will consider reliable? Because
I mean, like you said, for nearly all OB stars, if it's an individual object, you've got to accept that it's not, its position in the HR diagram is not a reliable indication of its single star evolution. So you're then talking about studying a group of stars, and if you've got a single object, you wouldn't trust it. But if there's a handful of objects, it becomes more trustworthy, if you know what I mean. Yes. So Cygnus OB2 is the region sort of I've studied the massive stars of the most, and got an idea of the ages there. There's a famous blue hypergiant in Sig OB2 called Sig OB2 number 12. It's one of the most luminous stars in the galaxy, but we don't know precisely whether it's a single or a binary or what its evolutionary or merger history is. So, you know, it's a sort of B3 supergiant, if I remember correctly. We don't exactly know if it's been following the right evolutionary path. So you'd obviously love to use that star as a sort of 120 solar mass star as a great age indicator for the system, but you can't trust one single star. So instead you end up going further down the mass function where there's some sort of late O-type giants that are just off the main sequence, that sort of their numbers are enough that you've probably got a good indication that there's a post-main sequence population in that association. It would be really interesting to see a model for a sort of population synthesis model, something like BPAS can do for an association's OB star population, where you take into account these facts and see what distribution in an HR diagram you'd get given some of these evolutionary pathways. But I'm going to guess the answer is going to be quite noisy.
Yeah, I guess. Okay, thank you. Any question, last opportunity? If not, then thank you very much once more, Nick, for this very nice review. Yeah, you will have the recorded version very soon in YouTube also. And next seminar will be not the last Thursday of December, because we'll be in the middle of the holidays, but will be 14th December, and this time will be Alex Gormaz, who will be talking about the impact of stellar winds on evolution. So hope you see many of you there. Thank you.
Thank you. Bye-bye.